Welcome to the master thesis presentation on short-term solar irradiance prediction for solar energy forecasting, presented by myself, Willem Himpen. So quickly, in overview, we'll first talk about what the problem exactly is, and second of all, what were the research results, and third of all, conclusions, recommendations, and future research. So this is a thesis collaboration with the University of Ghent and 3E, together with my mentors, Hassan and Philippe, and with Professor Benoit as my promoter. So what initially is the problem? Global warming is the main issue, the main problem, and it isn't the main issue that people are facing or humanity is facing on this planet. And what is global warming causing? It's causing air pollution, natural disaster, loss of infrastructure, and human capital. And because actually this big problem is going on, we see governments and people shifting more and more into adding solar and wind energy to the electricity grid, which as well has a result in the cost of these installation and systems has declined year over year. Because more and more of solar and wind is on the grid, will make as well the grid less reliable, because we can't perfectly predict when the wind is blowing and when the sun is shining. And because that makes the electricity grid more unstable, this as well will help increase the energy production of natural gas and other dispatch electricity sources. And because of that, will as well add, my apologies, will add as well more and more CO2 to the atmosphere, and it will cause more and more global warming. And it's a vicious circle that keeps going on. Now, what is the solution? As well, a vicious cycle, but a positive one. Once we have actually better solar irradiance prediction models, so this is mainly focused on solar energy, then we actually can better predict how much energy will be produced from those solar farms and other residential area. Then we will have a more reliable energy grid, and more incentives and subsidies and investments will happen into the solar industry, which results in more and more research and development, and more and more research and development will increase as well the performance of prediction models in the solar irradiance space, and it keeps growing and growing, which is a good outcome. So what is the research question? How can short-term solar irradiance prediction become more accurate with a data-driven approach with reduced latency and high reliability using only solar irradiance data? To sum it up, we'll use satellite data to actually put that into a deep learning model using the technologies of Python and the library TensorFlow to build our deep learning models. The three motivations that we have is, the two motivation is reducing greenhouse gas emissions originated from electricity production in combination as well with digitalizing and maximizing the asset value of renewable energy. The more and more we can maximize that asset value, the more and more people will start investing into renewable energy. And second of all, making the electricity grid more sustainable and stable with these renewable resources. The three sustainability development goals that are tackled here is affordable and clean energy, sustainable cities and communities, and climate action. So a literature overview. When we looked at the literature, we looked at two branches. First of all, weather data or weather prediction models, and then second of all, video prediction. Over here in the weather prediction models, you have the physics approach models and the data approach models. The physics approach models is where they literally try to use every molecule or try to predict all the flows of using data of temperature, humidity, air pressure, and so on, actually, to build a full model to predict the future states of the clouds. And a block matching algorithm, for example, is where they're going to match up two maps and try to see if certain areas have similar views, and then try to connect them with vectors to kind of predict the motion of clouds. And the data approach is literally a deep learning approach where only the data is inputted and the next frames or the next future states are outputted. And we saw as well with, for example, the first example, Google MedNet, they try to classify how much rain will be fallen in certain areas, and this actually outperformed even physics approach models, and has as well a very low latency. So this is probably a region or a direction where we'll go to with our model. And last, video prediction. A lot of video prediction, they first test their models on moving MNIST, so literally where you have numbers moving in a box. So this is a less complex environment. And this less complex environment makes it easier to test if your model works and to go to more and more difficult prediction, to more and more complex data. So in conclusion is we'll use a data-driven model for these 4 reasons. First of all, low latency. Second of all, we have the least amount of data that needs to be inputted, because, for example, with the physics approach model is a lot of extra data that needs to be placed in, but we're just going to use the solar radiance and try to predict the solar radiance in the future. And then the other 2 is it shows the best performance on short term, and as well the satellite data is has very high resolution and has also data correction and is standardized. And you can see on the right bottom where actually MedNet was outperforming HRR, or the high resolution rapid refresh, in the short term. So a data overview, or the steps with which data we're going to do what. First of all, we're going to start with a moving block into a box. After that, we'll go to a moving MNIST number inside of a still container. And then we'll add more and more MNIST numbers, and we'll add as well more difficult shapes. And the final step, we'll use the solar irradiance data. Now, the data pre-processing. We used min-max scaling to minimize or to get the data between 0 and 1, and we're using as well a 80-10-10 split, which means we used 80% of our data to train, 10% to validate, and 10% to test our data. And the solar radiance data, we've done the same pre-processing, and we used, like you can see here in the video, a moving block where we use a big map, and then we collected data over this big map. 2 regions, Algeria and Mediterranean. Most of our data was trained and tested on Algeria data because it's a very flat surface, and we can very accurately see the clouds past. And second of all, the Mediterranean, we tested our model as well on this data set to see if our model as well works in other environments. So now a little explanation on the architecture. We're using an autoencoder. An autoencoder is actually where we compress our data and then decompress our data to reconstruct our images or our frames, which represent future solar irradiance maps. So first of all, the first step is the spatial encoder. This spatial encoder uses convolutional 3D layers, and its main goal is just extracting as much features and much patterns from the data as possible over those 3 dimensions, time and width and height of the solar irradiance. And then second step is the spatial temporal encoder and decoder, where actually the data is implemented in convolutional LSTM cells, which is a combination of the previous one as a convolutional layer and as well an LSTM. And this LSTM, or long short-term memory cell, is actually learns from sequences, and this will be the layer that predicts actually the motion of the clouds. And after we did this step, we learned the motions of the clouds, and then after this step of the motion learning, we will put it into the spatial decoder. And what happens over here is this learned motion inside of a created kind of three-dimensional matrix is then again decompressed and is created the future frames of our solar irradiance again. Now, three types of predictions will be done. First of all, the 10-frame prediction. The 10-frame prediction is where we literally see on the top those 10 frames. Those 10 frames are the inputted frames, and then after that, our model immediately predicts the next 10 frames. Then the cutoff prediction is where we input our 10 frames, and we're trying to predict the middle red square because it's easier, because then, for example, clouds that are coming from outside that little box will come within that box, and it's easy because we have a smaller area for prediction. And then third is a 1-frame prediction, where we always input 10 frames which are the ground truth, and then we always try to predict only the next frame. And every time the next frame is actually the next 15 minutes. So the time interval between each frame of the solar irradiance data is 15 minutes. Now I'll go quickly over the results of this model. First of all, the block frame prediction is where we tested three things. First of all, does our encoder and decoder needs to be symmetrical? Answer was yes there. And as well, a spatial encoder, how can we optimize it best to create the best results? And as well, regularization, which resulted in improvement of our validation curve. After that, we used that benchmark model again to see if it the improved model on our moving MNIST data set, and we saw that the performance was okay. We added new learnings to it. We added batch normalization layer, different composition of the convolution LSTM layers, and then we as well did sensitivity analysis on the activation function and loss function, which was Leaky-Riley and the MSA who came out of that. And then as well, because you can see, for example, because we had more and more complex data, that the last frames over here, you can see in the middle with the 9 and the 3 moving objects prediction, become more and more blurry. And if we optimize the spatial encoder, so with more and more feature extraction, the model was better at keeping the shapes of the numbers. So that will be as well handy in keeping the shapes of the clouds. Now we converted that to extended moving, the extended MNIST data set, where we tested the kernels of the convolutional 3D layers and as well as the convolutional STM layers, which was both 5, bigger or smaller, performed worse. And then as well, we tested here 1-frame prediction, if this had improved results, and we even saw that every time we did multi-frame prediction, that kept the last 2 and 3 frames. It was hard to keep its shape, but with the 1-frame prediction, this problem was resolved. Now that we did all that previous research, we can jump in the problem of our solar irradiance data. And for some stuff, we had to start from the beginning. We checked what is the best epoch size, the batch size, how much compression can we do with this data, and then as well optimizing the depth width of both the convolutional LSTM and the convolutional 3D layer. And then the last thing as well, we used a pre-trainer. So what does that happen is we take different data, but from the exact same region, but from other years, and we kind of just straight train the pre-trainer, where we just encode the input frames and then try to predict the exact frames that were inputted. And by doing that with a lot of data, we can actually get our encoder to really to be really good and getting the features and information extraction from the data. And then once that was done, that model, we took the weights and the biases, or we took actually the encoder in a way, and we placed it into our model of predicting the future frames. And then we saw actually there was a much better performance, because already our model knew well how to kind of encode the data from data seen previously. It was not the same data. It was data from the same region, but from other years. So there was no kind of data that was already seen by the model initially. We saw that these models was performing okay. We could see that the clouds could be predicted and where they were, but they were still very foggy in comparison. Like you see, always the top layer is what we needed to predict, and the bottom one is what we predicted, and it was still not that accurate enough to be used in the real world. Then we actually made the problem a bit simpler, so we could see that it could be used. And the cutoff prediction, we saw similar results. That was still, it was easier for the model to predict, but still very inaccurate, the clouds that were passing by, and not strong enough to be used in the real world. So, but the best performing model that we do see a lot of possibilities with is the one frame prediction that you can see over here, where there's still a tiny bit blurriness, but that's very difficult to get rid of that. But the different steps we did here is, again, we've seen that the 10 frame model architecture works on the one frame, which it did, but as well, we used some more optimization on that. And then we used a pre-trained encoder to improve our results, plus as well regularization to get our optimized one frame prediction that you can see here on the bottom. Now, the discussion of our results and to compare that with previous research. First of all, the multi-frame prediction our model was 3 times better than the persistence model. And what is the persistence model? That's a model that just takes always the frame from the satellite frame before and just uses that to predict the next one. Because a lot of models use that as comparison. And we saw as well that the combination of optimized and pre-trained gave us the best results. But even much better results was the one frame prediction, which had much more accurate cloud shapes and had actually a little bit worse of mean squared error in comparison to the persistence model, but it was much lower than the multi-frame prediction. And again, using the pre-trained and optimized model gave the best results. Now, what is the conclusion? First of all, the one frame prediction is the best performing model and has the highest accuracy in the shapes of the clouds. And as well, it's kind of novel because previous research have either focused on different types of classification or regression problems, but not really on the one frame prediction model. The multi-frame prediction is limited. For my model, it's still only between 1 and 2 hours. After 1 or 2 hours, you see a lot of blurriness, and it's less capable of predicting. Then as well, a pre-trained encoder, which is something new that is shown here, which helps the model a lot in giving a boost to performance. And then as well, we see that deep learning is a viable approach to this model of short-term solar radiance prediction. The only thing is, we do see that using maybe other types of data of kind of physics approach models would help if it was a combination. And then lack of computational resources, which means is I used the GPU lab of a university and as well the Google Colab environment, and sometimes as well that gave out of memory errors because we're with very high dimensional data, that can sometimes give problems in the memory. And last but not least, the model has potential to be generalized because once we tested the one frame prediction model from the Algeria side as well to the Mediterranean side, we saw that it was performing decent. It was performing similar actually as the over the Algeria site. So it has potential to be generalized. Now, future research and 3 recommendations. First of all, data improvement. Obtain more data from similar regions and more years and more computation power would definitely help the model. Second of all, use data augmentation to create more data. So, because a lot of cloud data was very sometimes very similar, so with a little bit skewed or shift in movement of the clouds would help as well generate more data, and as well adding more channels. Currently, we only use one channel, the solar irradiance data, but besides that as well, if the time would be added, the temperature, air pressure, air pollution, wind speed, and so on. This would help as well to give more a diverse form of data to the model and would help it a lot. Then second of all, in the spatial temporal encoder, we always use the convolution LSTM cells, but it could be as well smart to use the convolution GRU cells, because new research actually has shown that this is a lot is better. And third of all, the hybrid approach, like I mentioned before, is an ensemble model of physics approach and a data approach combined, so that you have the best of both worlds. Voila, that is actually the wrap up of my master thesis on short-term solar radiance prediction for solar energy forecasting. So hopefully you enjoyed it, and if there are any questions, feel free to contact me. Thank you. Bye bye.